let's do some more limit examples. So let's get another problem. See, if I had the limit as x approaches 3 of, let's say, x squared, let's say minus 6x plus 9 over x squared minus 9. So the first thing I like to do whenever I see any of these limit problems is just substitute the number in and see if I get something that makes sense, and then we'd be done. Well, usually we'd be done. I don't want to make these sweeping statements. If the function is continuous, we'd be done. But let's say, if we put the 3 in the numerator, we get 3 squared, which is 9, minus 18 plus 9. So that equals 0. And then the denominator also, see, 3 squared minus 9, that also equals 0. So we don't like having 0 over 0. My pen tool is malfunctioning again. So we don't like getting 0, 0, 0. So is there any way we could simplify this expression to maybe get it to an expression that when we evaluate it at x equals 3, we actually get something that makes sense? Well, whenever I see two of these polynomials here, and they look, just by inspecting them, relatively easy to factor, I like to factor them out because maybe there's the same factor in the numerator and the denominator, and then we can simplify it. So let's say that this is the same thing as, let's see, that looks like it's x plus 3. No, x minus 3. That's a minus. Let me scratch that. This is x minus 3. It actually looks like it's x minus 3 squared, but we're just going to write x minus 3 times x minus 3, which is, of course, x minus 3 squared. And then the denominator, you know how to factor these. This is x plus 3 times x minus 3. All right? So the limit as x approaches 3 of this expression is the same thing as the limit as x approaches 3 of this expression. And of course, this there's nothing we can do to change the fact that this function or this expression is undefined at x equals 3. But if we can simplify it, we can figure out what it approaches. Well, if we assume that x is any number but 3, we can cross out these two terms, because then they wouldn't be 0, right? It only is 0 when x is equal to 3, so in the numerator and the denominator, we could cross this out. And we can say, and I'm not being very rigorous here, but this is kind of how it's taught, and I think you get the intuition, that this is the same thing as the limit as x approaches 3 of x minus 3 over x plus 3. Now let's just try to stick the x in and see what we get. Well, in the numerator, we get 3 minus 3. We still get 0. But the denominator here, we get 6, right? 3 plus 3 is 6. So now we get a good number, 0 or 6. Well, that's a real number, so it's 0. 0 or 6 is 0. So that was interesting. The first time we did it, we got the answer 0 over 0, and now we get the answer 0 by simplifying. But of course, it's very important to remember that this expression is not defined at x equals 3. It's defined everywhere but if we were to graph it, and I encourage you to do so, you would see that as you get closer and closer to x equals 3, the value of this expression will equal 0. And I know what you're thinking. Well, this was 0, 0. Is every time I get 0, 0, is every time I get 0 over 0 going to end up just becoming 0 when I evaluate the expression? Well, let's explore that. Let me clear this. Let's say, what is, my pen is not working. Okay, the limit as x approaches 1 of, let's say it's x squared, let's say it's x squared minus x minus 2. All right. Now let's say x squared plus x minus 2. As you can see, I do all of this in my head, and I'm prone to mistakes. And all of that over x minus 1. Well, once again, if we just evaluate it, let's what happens when x equals 1. You get 1 squared plus 1, so it's 2 minus 2. You get 0 over 0. So once again, we get 0 over 0, and we have to do something to this, maybe, to simplify it. Well, let's factor the top. So that's the same thing as the limit as x approaches 1 of, well, that's x minus 1 times x plus 2, right? It's 2x, x minus 1 times x plus 2, and x minus 1. And I think you'll often discover when you see a lot of limit problems that even if this top factor, if this top expression is hard to factor, chances are one of the things in the denominator that are making this expression undefined is probably a factor up here. So sometimes you might get a more complex thing that isn't as easy to factor as this, but a good starting point is to guess that one of the factors is going to be in the bottom expression, because that's kind of the trick of these problems, to just simplify the expression. So once again, if we assume that x does not equal 1, and so that this expression would not be 0 and this would not be 0, then these two could be canceled out, and we get that this is just the same thing as the limit as x approaches 1 of x plus 2. Well, now this is pretty easy. What's the limit as x approaches 1 of x plus 2? Well, you just stick 1 in there and you get 3. So it's interesting. When we just tried to evaluate the expression at x equals 1, we got 0 over 0. And in the previous example, we saw that it evaluated out when you simplified it to 0. And in this example, it came out to 3. And I really encourage you, if you have a graphing calculator, graph these functions that we're doing and see and show yourself visually that it's true that the limit as you approach, say, x equals 1, actually does approach the limits that we're solving for. And make up your own problems. Hell, that's what I'm doing. So you could prove it to yourself. So let's do another. Let's do one that I think is pretty interesting. Okay, there you go. All right, let's say, what's the limit as x approaches infinity? The limit as x approaches infinity of, let's say, x squared plus 3 over x, where'd my pen tool go? Over x to the third. So the way I think about these problems as approach to infinity, just think about what happens when you get really, really, really large values of x. And kind of a cheating way of doing this is if you have a calculator, and even if you don't have a calculator, put in huge numbers here. See what happens when x is 1,000,000. See what happens when x is 1,000,000,000. See what happens when x is 1,000,000,000,000. And I think you'll get the point. You'll see what, if there is a limit here, you'll see what it's going to. But the way I think about it is, in the numerator, kind of the fastest growing term here is the x squared term, right? This is the fastest growing term here. In the denominator, what's the fastest growing term? Well, in the denominator, the fastest growing term is this x to the third. Well, what's going to grow faster, x to the third or x squared? Well, yeah, x to the third is going to grow a lot faster than x squared. So this denominator, as you get larger and larger and larger values of x, is going to grow a lot faster than that numerator. So you could imagine if the denominator is growing much, much, much faster than the numerator, as you get larger and larger numbers, you're going to get a smaller and smaller and smaller fraction, right? It's going to approach 0. And so as you go to infinity, it approaches 0. I know that's I kind of just hand waved, but that's really how you think about it. Another way you could do it is you could actually divide this fraction. You could actually divide this rational expression, and you'll get something like 1 over x plus something, something, something. And then you'd also see, oh, well, the limit as x approaches infinity of 1 over x is also 0. Let's do one more. I think I have time. I'll do this fast so I can confuse you. The limit as x approaches infinity of, let's say, 3x squared plus x over 4x squared minus 5. These problems kind of look confusing sometimes, but they're really easy. You just have to think of what happens as you get really large values of x. Well, as you get really large values of x, these small terms, these ones that don't grow as fast as these large terms, kind of don't matter anymore, right? Because you're getting really large values of x. And in this case, these don't matter anymore, and then these two x terms grow at the same pace, right? And they'll always be kind of growing in this ratio of 3 to 4. So the limit here is actually that easy. It's 3/4. So what you do is you just figure out what's the fastest growing term on the top, what's the fastest growing term on the bottom, and then figure out what it approaches. I mean, if they're the same term, then they kind of cancel out, and you say the limit approaches 3/4. It's a very non-rigorous way of doing it, but it gets you the right answer. See you in the next presentation.